So welcome this afternoon. Nice to see you all on site and online. I'm very delighted to welcome Dr. Sébastien and Marcel with us today. He's a senior researcher at Idiap Research Institute, where he heads a research team and conducts research on face recognition, speaker recognition, vein recognition, and presentation attack detection. His talk today is titled Face Presentation Attack Detection. To give you an idea of what to expect, we have 60 minutes in total for this seminar. Marcel told me he planned for 45 to 50 minutes for his talk. There's a slight preference to address all questions rather at the end, so please feel free to put the questions in the chat. We will then try to take them up at the very end. Before I dive into the presentation, I'd like to express my sincere thank you once again to the CIS team for organizing this event, and I welcome Marcel. It's good news for me.
Thank you. Thank you very much. Okay, so good afternoon, everyone. So, right, here we go. Good. So my name is Sébastien Marcel. So I'm from the Idiap Research Institute, and today I'm going to give a presentation about a topic maybe we are not very familiar, which is presentation attack detection, more particularly face presentation attack detection. This is a kind of an overview talk about the topic, and there's going to be the outline of presentation. So I just have a quick, short introduction about what we do, about the team at Idiap, a quick recap of what is biometrics, then what we're talking about, which are presentation attacks, some examples from the reality, and then I will go on until examples of how to detect attacks. So the group, about the group. So, so the BSP group stands for Biometric Security and Privacy Group. And basically what we do is signal processing and machine learning, deep learning applied to BSP. So either to recognize people using their biometric characteristics, so face, speaker, vein, gait as well, or EEG signals, but also recognizing some attributes such as gender, age, and other things. There is another big area of research, which is on the security angle, where we are interested in to detect presentation attacks, but also we are looking at other forms of attacks such as morphs, deepfakes, and so on. We're also working on privacy protection aspects, so developing algorithms to protect the templates, the biometric templates which are stored. Also, since we are dealing with multiple biometrics, we're interested into fusion, and nevertheless, since we are using a lot of AI algorithms, we are interested in all the aspects of fairness of those models in the context of, let's say, face recognition, for instance, and other things. And overall, what we try to achieve here is work which is reproducible with systematic software and data, public data, which is distributed along our research papers. So the staff is composed of 7 research associates from different origins, 2 postdocs and 4 PhD students, including 3 PhD students, who are enrolled at EPFL. So as I say, I will have a quick intro about what is biometrics. So biometrics is a science of establishing the identity of a person based on a number of attributes, can be physiological, behavioral, or chemical, such as the DNA, for instance. And let's say the main challenges we have in biometrics, in the biometric technologies, is that, so some people might think that this is a solved problem, which is actually not, because there is still a number of difficult challenges that must be overcome, in particularly how to deal with intra-class variability, preventing from presentation attacks, protecting from the biometric templates. Just a couple of examples, well-known traits, biometric traits for the physiological part: fingerprint, face, iris, and retina, including veins. Behavioral, we can consider gait, of course, but the way you type on the keyboard, the way you sign your signature, and voice also can be considered by some people as behavioral biometrics. Applications, many applications actually. So first applications, I would say, in biometric science, mostly for criminal identifications, but actually many other tasks in the forensic context. Government applications, obviously, so biometric passports, e-passports, other national programs in India, for instance, e-voting, digital identity, these kind of things. Commercial access control, how to unlock your phone, log into your computer, withdraw cash from an ATM, or to pay over the internet, and other forms of physical access control using biometrics. And finally, we also find a couple of applications in the entertainment industry. So, in short, what is biometrics? A biometric recognition system works in two stages. There is always a first stage, which is the enrollment step, where you associate a biometric with an identity. And then you have the second step, which is the recognition, which is checking the identity either via identification or verification. So you just always have one of those two cases. Either you want to answer the question, who is this person? In which case you do a one-to-many comparisons. Or you want to achieve verification and you want to answer the question, is this person really who they say they are? And you do a one-to-one comparison. This is either one or the other. And overall, the architecture of biometric system is the following. You have a sensor that receives data from the real world. This biometric data, which is digital data, is sent to the feature extractor module that processes data and generate biometric features, which are stored in a database during the enrollment process, the enrollment stage. And later on, at the recognition step, this biometric features is compared to the biometric reference, the comparator, that produces a score that goes to a decision module that takes the decision either to verify or to identify. Easy. Problem is that those systems are subject to vulnerabilities. So here you have a number of vulnerabilities that have been identified in the literature. So you have basically direct attacks, number one, which are also called presentation attacks or spoofing. And you have the indirect attacks, which are all the others, can be attacks at the channel, and the communication channel to intercept data. It can be at the software level to alter the modules. It can be also accessing the data in the database to steal it or to manipulate it, because data is at rest and you have plenty of time for this. Today, we are going to talk about presentation attacks only. So attacks at the sensor level, number one. Then we're also going to focus exclusively on biometric systems using face information, basically face recognition. And we are going to look at a couple of methods to detect presentation attacks, so those attacks. And the field is referred to as presentation attack detection, or PAD for short. A couple of definitions before I continue. So presentation attacks, so this is a term I've used. So a presentation attack is an attempt to fool a biometric system by presenting a fake. And there are two purposes. Either you want to impersonate someone, you want to steal the identity of someone, or you want to avoid recognition, and you want to obfuscate your own identity. And then, therefore, you have the task of determining if what you present is a presentation attack or not, in which case we refer to this as a PAD, presentation attack detection. And two of the terms I need to introduce, you will see we are going to use later, is the term PAI for presentation attack instruments. This is basically the biometric characteristic of the object which is used to launch a presentation attack. For instance, a face mask. Here you have a couple of masks that I took for you if you want to have a look later. But you can use also gummy fingerprints, dead body parts for the biometrics. And on the other hand, you have what we call a bona fide presentation, which is a normal interaction of the subject with the system. So everything which is not a presentation attack. And this terminology comes from the standards which are used in the community. So why this topic is important? This topic, so presentation attacks actually are a major threat to biometric systems, because actually the attack is performed external to the system. So the attacker doesn't need to be an expert or to know exactly how the system works in order to launch an attack. So it basically can be done by almost anyone. And you will see anyone can do it. This is also a growing field of research. We have many novel methods for innovative presentation attack instruments or presentation attacks, which are proposed every year. There are novel techniques and algorithms for PAD that can be proposed, either using different sensors. So also looking at signal processing, machine learning, and all the aspects of generalization, in particular to unseen attacks. And it's not only for face recognition, but it's also for other biometrics. Right, so I'm going to review a couple of examples, a few examples from the reality. I told you that anyone can do it. These are college students in China trying to spoof a face recognition system protecting lockers that were protected through face recognition. So here, a user use a locker, a public locker, and to lock his stuff with face recognition. And like you do in Disney, in some places, you can use face recognition to put your belongings in a safe. But actually, some kids, they found out that simply they can put a picture of the someone in front of the camera, and boom, it unlocks. Right, so anyone can do it. Robbery. So this is an example of impersonation, sorry. This one, interesting case. Actually, I have a couple of other cases like this. So where do you have this guy that robbed a couple of banks in the US by wearing this silicone mask of this black guy, so the same as this one, but black, to avoid identification. So this case of obfuscation. This one, a case in immigration. So this young guy, boarded a plane in Hong Kong to Vancouver with the mask of that old person. He was seeking asylum in Canada, and then he simply boarded the plane. And then during the flight, he removed the mask, but he just managed to pass the security with the boarding pass of someone else. Face unlock. So it was shown that it could be spoofed, attacked by presenting a face image displayed on the screen of another smartphone in front of the smartphone. So it was 2011. 2017, the iPhone 10 released face recognition to unlock the device. Also, it has been mentioned to be spoofed, attacked successfully at that time. So these are examples from the reality. We come back a bit more to science. We are going to review in turn a number of presentation attacks, instruments, so objects or methods to create an attack that have been shown to be all successful and that have been shown to be all published and evaluated in the literature. So the easiest is simply the print. So I'm not going to, I won't have time to give all the details for all the techniques. So you'll find all the details in the papers, in the link at the bottom. So here, this is the most basic attack you can do, is an attack with a piece of paper. You just print a face image on paper and you show it to the camera, and that's it. You can bypass the face recognition system. By extension, you can also consider using another medium, which is not the paper, which is just a screen. It can be a small screen, a large screen, whatever. And then the camera from the, let's say, the smartphone here in front of the device just sees the face on the screen and try to recognize it. So you can present an image, you can present a video, you can present a deepfake, you can present whatever. And actually, that's pity there is no more people in the room because it is typically good for real-time quiz in person. So I'm going to ask the question to some of you guys in the room. Can you tell which one? So this is an image as seen as the camera of the smartphone here. Okay. So the camera sees faces which are real and faces which are not. Can you guess which one is real, which one is fake? I'll just give you 10 seconds because I don't have much time.
Is that the shadows, maybe?
So which one? So let's say the first row. So fake, then
Then they're gonna right?
you don't know. Third one. Okay, shadows. You say so fake. Here.
No, it's the
Real.
Not fake. Real.
Okay, fake, real.
You're going one by one.
Yeah, one by one. Yeah. Okay, and any other guess? Right. Okay. No, they're all fake. They're all fake. The only difference is that, so by column, you have the same data subject, of course, but what has changed is the original image that was taken to be displayed. So in one case, the original picture was taken on the uniform background, and then the second row, on a complex background. And then you use this picture, and then either you print it, and you display the print, or you display it on a small screen, and you show the screen, or you display it on a larger screen, and you show the larger screen. Okay? So here what happens is that if you look carefully, the first column, you are going to see printing artifacts from the printer, because here it was an inkjet printer that was used. So you have printing artifacts from printing. Then the second column, you have images which are a bit more blurry. The color is also not right. And then this is because the screen is very small, because this is a screen of a smartphone. And if you want to make sure that you don't see who is wearing the phone right in front of the sensor, you have to come very close to the camera, right? So therefore, this is why it is blurred. But if you are at the right distance with a large screen, you're not going to see the border of everything. You can get very good quality attacks. So as you see, it is challenging for humans. Second attack level is going 3D. So here the idea is that you can manufacture 3D masks. So you can 3D print with any printing service a 3D mask. The mask can be plain or with the holes. So you can do eye blinking, whatever. And you present the mask to the recognition system. This attack was published and shown to be successful in 2014 already. You can move to better quality masks. So these are examples of hyper-realistic masks. Here I just took two, so you can have a look. So here on the desk here, so two hyper-realistic face masks that have been shown also to be a challenge, and which are interesting to be detected. So you can see the quality has improved over years. Another level is going in using a different type of material. So, and a particular material of particular interest is actually the silicon. The silicon has these particular properties to, let's say, not imitate, but to look like human skin, at least from a spectral point of view, at least in the near-infrared domain. It also absorbs heat, so it's flexible. So as a difference, those masks which are rigid. So silicon masks also, they are the favorite attacks of the bank robbers, right? So they love those kind of things. So this is something that we investigated at some point, but it can mostly be used to obfuscate identity, right? So at least those type of masks. But we were interested to do to see if we can do impersonations with those masks. So we also created customized silicon masks for specific people we know. Okay, so we have been able to manufacture about a bunch of nearly 20 masks that we have used in our studies that are published here. So same thing, you manufacture a 3D mask, you present the mask, and you simply verify if there is a vulnerability. I will give a bit more details later on how we do this vulnerability analysis. And finally, because I wanted to go fast on different types of attacks, you have other forms of attacks that are emerging, which are actually challenging, is first makeup. Makeup can be used to change your appearance. Either you can, if you're a very skilled artist, you can change your appearance so you could look like, let's say, a character of a famous TV show, right? That some of you may recognize. For the others, maybe because you're not geek enough. And all that you can use also makeup to obfuscate your identity by, for instance, simulating aging. So you can age your face with just makeup. And at some point, it means that face recognition won't work anymore. So here you have left to right, you have different levels of makeup that have been applied to the same person on the same day. Yep. That's crazy. Yep. That's pretty impressive. Right. Other forms of attacks you can do will be manipulating the data that you will display. For instance, you can investigate morphing. So morphing is combining two identities into one. You can do deepfakes, face swaps. So here you have face swap, right? So you can, but if you see the three images, you can find, you can figure out which one is the face swap. This is the one in the middle. So this is a face video of the first person where we swap the face. So this face of the third person is onto the video. This is the best we can do. This can be done in real time on videos, and you can do also the voice conversion at the same time. So you can generate audio-visual deepfakes at the moment. And this is quite impressive. And therefore, you can do presentation attacks because you can impersonate someone with this. So these are threats and things that needs to be detected and addressed. All details you can find in the publications below. Right. So there was just a sneak peek about how to create attacks, which is one part of the job. To stay ahead in the race of making attacks. So we play the bad guys first, and then we try to play the good guys and try to come with ways to detect those attacks. But before I present some techniques, I'm just going to give a bit of perspective on how we evaluate all this, right? Because we have a biometric system. Let's say we have a face recognition system, we want to recognize faces of persons and not recognize the face of someone else. And now we have also presentation attacks. So how all of these interplay, right, all together. So first thing we have to understand is that what we have is, let's say, a face recognition system whose goal is to say yes or no. Yes, this is the same person. No, this is not the same person. So typically you present bona fide data. So bona fide data can be someone already enrolled in the system or not. And if this person is enrolled in the system, you should accept. If the person is not, you should reject. Okay, and then typically you have two errors and you compute those two errors to say if the system is good. If the system is perfect, you are going to have no error, so false match rate of 0 and a false non-match rate of 0, which in practice never happens because there is always a price to pay. So always one error is present. Also, we have those two errors when we only have bona fide genuines or bona fide zero front imposters. But when we have an imposter that make a little extra effort, therefore that we call presentation attack, what's going on? Well, what's going on is that this attack is going to be injecting the biometric system. The biometric system won't have any choice but to classify this one as either accept or reject. So there is a chance that this attack, because it looks like someone which is enrolled into the system, is going to be accepted. And the way you can visualize this by simply looking at the score distributions of the output of, let's say, a face recognition system. So you could plot the score distributions of genuine genuine scores here in blue. You could plot the score distributions of the zero effort imposters here in red. You would observe that the two are separate. This is why face recognition works, because you can recognize and separate real identity, enrolled identities from others. But if you would present fakes that looks like someone who is enrolled, then those scores will exceed the matching score, and then you will accept simply a portion of those presentation attacks. So the higher this portion is, the higher the vulnerability is. And you can simply measure that by counting the number of attacks. So you can call it spoofing false accept rate, or another term, EAPMR, here, which is another term from the community. What we have done is that recently we have conducted a study to investigate whether the current face recognition technologies, which are so-called the deep face recognition, face recognition technology based on deep learning, on deep architectures, which have been shown to be really accurate. So it has changed really. It was a game changer in the industry. Those face recognition systems based on AI models. And we investigated those to see if they would be more vulnerable or less vulnerable to presentation attacks than previous systems. And actually, what we found out is that those systems, which are extremely accurate, very good at recognizing faces, are actually very vulnerable. It's easier to spoof them, to bypass the recognition system with a fake, those systems, than other systems of previous generations. Now, this was only the first part, the traditional recognition system, which is exposed to bona fide samples to be recognized or rejected, but also presentation attacks. But what we want to do is to detect those attacks, okay, and in order to reject them. And what we're going to have is that this module is going to be actually another classifier, which is going to take either bona fide samples, so real people, and presentation attacks, and should be able to make the difference. You should be able to tell this is a bona ID, this is a real person. So the exercise that you try to do during the quiz, you would like to ask a machine to do it, whether this face image is a real person or fake. Since this is a binary classification task, we are going to have two errors we want to minimize. They have their own teeny little names from the terminology which is used in the community. So this is not important to remember the names, but we have two errors that we just measure, and when the two errors are low, then the classification task achieved by the PAD subsystem is acceptable. Overall, there are three ways to detect attacks, three categories of methods. Either you have the software-based, what I call the software-based methods. So these are techniques that are going to use the same biometric data from the sensor that is used to do the recognition part. Let's say you have a camera, a color camera that captures your face image to do face recognition. You're going to use the same data to also do PAD. First category. Second category, hardware-based. So here we are going to rely on additional sensor to capture all the data, right? for the PAD task. For instance, you could have a thermal camera, let's say, in addition to the color camera, to capture your thermal signature and use that for classification. And then you have a third category, which is challenge response, where you have an interaction with the user and you prompt the user to do something, say something that cannot be, that is not predictable, right? So that you can, on the spot, be sure that you are not going to have a machine or an attack. So here in the rest of the presentation, I'm going to focus on examples from the literature on papers and techniques we have published, only for the software-based case and the hardware-based case. Software-based first. So what I mean by software-based first in the context of face PAD is that we use traditional sensing systems which are used for face recognition, which means RGB cameras. So you have RGB data. We have a number of data sets that exist in the literature where for each data set, you have on one side bona fide samples and attacks which are classified by different types. You have prints, replay, masks of different material. Even you have a database with fake faces which are made of wax that come from wax museum, for instance. So mostly celebrities. So you have a number of databases that exist like this on which you can train, test, and evaluate PAD system. So over the years, initially when we started to work on this topic 10 years ago, we started looking at traditional approaches combining signal processing and traditional machine learning. So we published and people also explored the use, let's say, of motion. So for instance, using computing the optical flow in the video sequence around the face region and looking at the correlation between the motion of the face image and the motion of the background that you feed. So you form your features, you feed that to a normal traditional multi-layer perceptron, let's say, and you train a classifier to detect a bona fide sample from a photo attack. It has been shown to be successful at the time. Then you can go a bit further. You can look at, try to investigate texture. For instance, someone in the audience has been able to spot there was something weird in some of the images with those lines here. Typically, if you do some texture analysis, you could capture this kind of teeny details that you have some artifacts you may have in the, let's say, printing process. And you can use texture descriptors, which are used in computer science, computer vision. So for instance, the local barring patterns combined with traditional classifiers or SVMs support victim machines to also detect static attacks from and real attacks. Sorry, static attacks like prints and dynamic attacks such as replay, for instance, videos, for the task of bona fide versus presentation attacks. You can also investigate the use of general image quality measures, again, combined, use as descriptors and combined with traditional classifiers. And all these have been explored, let's say, a bit more than approximately 10 years ago. Then came a changer. So this is where we were investigating uncrafted classifiers. Then at some point, we have been investigating the use of deep learning architectures. So one of the very first that we explored was, of course, deep convolutional neural networks. In particular here, we used DenseNet architecture that was pre-trained on image classification tasks that we fine-tuned for a task of presentation attack detection. And what we have shown and what we have seen and observed as very quickly is that these kind of methods outperform completely the previously best performing systems that were using local barring patterns or image quality metrics. Later on, we also investigated more advanced architectures such as vision transformers. And these have been shown to outperform the CNNs on another scenarios, in particular a generalization scenario where you don't see some attacks. So you train on some attacks, you exclude other attacks, and you test whether your model, your PAD system can generalize on detecting attacks you have never seen before. Let's say you train them on only replay and prints, and you see if you can detect masks, these kind of things. This is it for software-based. So here the list can goes on, and actually you can find plenty of papers with different ways, different type of architectures. It's at the end of the day, it's always the same story. It's always the same task. You should classify bona fide versus presentation attacks. The only thing that change is the architecture, the type of databases which are used, the loss you play with, etc., etc. And then the second direction I like to, and it will be the last one, and almost I'm on time. That's perfect. Is the hardware-based. So this one also is quite interesting. So here, as I say, the idea is to use another additional sensing that you will not use to do recognition. So let's say you do face recognition with the RGB camera, but here you like to do PAD with other things. The problem is that you don't know what are the other things that works, because there are many things you can explore. You can look at near infrared, but in which case, which wavelengths? You can use that. You can consider shortwave infrared. Same thing, which wavelengths? You can use depths. Okay. You can use also thermal imaging. So here, what we did is that we built a sensing station, which allows to capture in a synchronized way all this together. So we're able to capture high quality RGB, high quality near infrared in 4 different wavelengths, from 660 nanometers to 940. We also had a cheap off-the-shelf stereo sensor to capture the depths, but we're also able to reconstruct the depths from the near infrared cameras, because actually we have 2 near infrared cameras mounted in stereo. We also had 2 thermal cameras. We have 1 high quality thermal camera and a very cheap thermal camera, the kind of cameras you plug with a micro USB on your phone. So these kind of cameras, which actually produce very low quality signal, but still could have been investigated. And also using a high quality shortwave infrared camera, where you can capture the wavelengths from 1050 nanometers to 1650 nanometers. And with this, all this data, you can study different forms of combinations and try to answer a different number of research questions. Whether near is better because maybe in some attacks there is no metallic ink that can be used, or is silicon can be detected with near? Is silicon can be detected better with thermal because it absorbs heat? You know, these kind of things. So with this kind of data and coming from this kind of sensors, we could also explore continue to explore deep learning-based architectures, as we have seen, but this time combining different channels, because we have near, but not only. We can combine near, RGB, shortwave infrared, or maybe depths in many ways. We propose a number of different architectures over the last years. For instance, here we have an architecture that we call CNN, for multi-channel CNN. So basically, the main idea is that we use a backbone face recognition network which is the one at the top. We decide to freeze the deeper layers that will be shared, and actually that will be frozen. And on the opposite, we have the duplicated input layers, which are typically the first convolutions, which are the closer to the domains. They are going to be adapted depending on the domain you present. So either you present a near infrared or thermal channel. Altogether, we learn at the end a final MLP head with a traditional contrastive loss, for instance, for the task of presentation attacks versus bona fides. Later, we have been exploring, because we wanted to explore the possibility to detect unseen attacks. We extended this approach by adding an additional loss, in particular to add one class comparative loss in the concatenated embedding produced by the different architectures here, in order to learn a compact representation. So here, the idea is that in this embedding space, we want to make sure that all the bona fide are going to be pulled together and all the presentation attacks are going to be pushed away from the center as much as possible. And then with this, once the embedding is trained, you have this representation, you can use simply traditional statistical models, such as, let's say, a Gaussian mixture model, to model the distribution of those compact embeddings. And we have been able to show that we can gain some generalization with those approaches. This was later extended with also with the same type of architectures, but using different forms of losses that have been published here and respectively in IEEE TIFFs and here in CVPR. Right. So couple of conclusions, something we have learned from all these experiments, especially on the hardware-based, which have been able to push really the frontier between into the quantity of attacks, different types of attacks we can detect. We have been able to show that sometimes even simple average of temperature of face regions can be effective to detect very simple attacks, but not more complex attacks. If you have more complex attacks, such as, let's say, masks made of silicon, actually this is not effective anymore. We've been able to show that so we can detect the majority of the attacks. So here we have different types of attacks. We have the attacks for impersonation and also obfuscation. We have two forms of attacks here. We've been able to show that we can detect the majority of them just using shortwave infrared spectrum, okay, or an appropriate combination of RGB and near. Now, this is not, there is a catch with that, is that those shortwave infrared cameras, they are very, very expensive. They are let's say, almost 10 times more expensive than RGB plus near. So, so there is a price to pay. Also, with this shortwave infrared, we have been able to find that actually the best wavelengths, or the combination of different wavelengths around 1,450 nanometers, provide the most accurate classification, the best classification rates between presentation attacks and bona fide. And actually, which is actually, and the important point is that if you look at the spectral distribution, the wavelength absorptions between skin and the other objects, you see that actually the water absorption, around the water absorption in the shortwave infrared. This is why it works very well. Okay, so that's about it. I'm going to conclude and give the floor for questions. So is PAD a solved problem? So I would say that no, it's not yet a solved problem, because since we have biometrics, which is becoming more prevalent in many applications, there will be more and more incentives for people to launch presentation attacks and to find innovative ways to bypass those systems. So PAD research is an active research field, because one of the main issues is generalization, especially a generalization to unseen attacks. An example I've often take is that if I create an attack recipe that I use to create attacks, and I give the exact same recipe to another lab to create the same attacks, although we follow the same recipe, the PAD system that will be trained and tuned on one side won't generalize to the other. So there is still a lot of work in this area. Maybe it's just because there is not enough research databases that have been published. It's difficult to tell. And then to conclude, in case you're interested by this topic, you can find there is a reference book on the topic. There have been there was a special issue in SPM a couple of years ago, and there is also a survey in PAMI that you can refer to. Thank you very much for your attention, and I'm open for questions. Plenty of time.
Just some brief words of closing. Thank you very much for your very interesting talk. I'd like to thank all of you on site and online for being with us today. Just a brief heads up. So we would be delighted to welcome you on the 31st of May for the colloquium with Peter Velikovic. Sorry for that. He's from Google DeepMind and also affiliated to University of Cambridge, and he will be on campus 31st of May at 11 in the mornings in BM 5202. So in person or online, we would be happy to welcome you. And of course, we hope to see you then again in June for our next CIS Get to Know Your Neighbor seminars. Goodbye.